Okay, hi everyone. So I'm Weiqiang. So today I'll talk about direct sum for parity decision trees. So this is joint work with Tyler and Siyao from NYU Shanghai and Mika Gilbert from EPFL. Okay. So I want to start my talk with telling you what is direct sum. So let's say be some complexity measure that we are caring about. So for example, it can be decision tree depth or circuit size. So usually the cost of computing k copies of functions is at most k times the cost of computing one copy. So direct sum is saying that, okay, for every function f and the integer k, the cost of computing k copied functions is almost equal to k times computing cost of computing one copy. Okay, so for example, if computing function f needs decision tree of depth d, then what about computing k copies of functions? Well, we know that, okay, decision tree depth of kd would be enough, but direct sum is saying that tree of depth much smaller than kd cannot compute. Okay. So I want to talk about some backgrounds. So this direct sum actually has been extensively studied for many computation models, and two prominent ones are first ordinary decision trees, and we know that, okay, this direct sum holds perfectly for ordinary decision trees in both deterministic and distributional setting. And by Yao's minimax lemma, we know that the later implies randomized direct sum. And the other is a communication complexity. And different from decision trees, the deterministic direct sum is widely open, and for the best bound, there's a square root loss. And for distributional direct sum, actually the bound depends on the concrete distribution. So for product distribution, we know this direct sum almost holds just up to a log factor. And for arbitrary distribution, it's open, and the best bound, for the best bound, there's still a square root loss. And there's still one thing I want to mention is this discrepancy. It's a very old result. So discrepancy is some like lower bound for randomized communication complexity, which I'll talk later. And it's actually a very old result. I think 15 years ago, it shows that this discrepancy actually, this Axel lemma, which is like an even stronger version of direct sum, holds for discrepancy. So now I want to talk about some motivations. So why we care about direct sum? Actually, this direct sum serves as you can see a cornerstone of many interesting things in complexity theory. So for example, if you want to prove deterministic direct, if you want to prove some composition theorem, first you need to prove deterministic direct sum. And if you want to prove XOR lemma, you first need to prove direct product, and to prove direct product, you need to prove randomized direct sum. And all these things has numerous applications in complexity theory. For example, circuit lower bounds, de-randomizations, hardness amplifications, and time-space trade-off in cryptography. Okay. And the focus of the talk is randomized direct sum for the following model, so-called parity decision trees. So what is parity decision trees? Oh, okay. So parity decision trees is an extension of ordinary decision trees. So each time we can actually make a parity query by choosing arbitrary subset S and ask the parity of variables with coordinates in S. So for example, we have a parity decision tree here, and for this input, okay, we can first make query x1 XOR x3, and we find it's 0. Then we make the query x1 XOR x4, and then this 1, and so on and so forth. And then we end up at a leaf, which is accept. Okay. So the parity decision tree complexity of function, just the depth of the shallowest parity decision tree that computes F. And here the definition of computes depends on whether it's deterministic, randomized, or distributional, just like all other computational models. And we know that this model, the power of this parity decision trees, is actually sandwiched between ordinary decision trees and communication protocols. Okay. Okay, so now I want to talk our first result. So our first result is actually we prove that this direct sum holds when the hard distribution is product. And to be more formal, we define this D product F at the maximum distributional complexity of F with respect to mu, where mu is over all product distribution. And we prove that even for every search problem and integer k, the randomized parity decision tree complexity of computing k copies of F is at least k over log n times D product F. Okay, now I want to talk about our second result. So before talking about it, I need to define what is discrepancy. So actually, it appeared in 80s to first appear in 80s to prove randomized communication lower bounds. So for convenience, I'll define this. I will write the protocol pi and the function f in +1 - 1 basis. And so given pi f and the distribution mu, we can write. So this is basically the correlation between pi and f. So we want to we want it to be close to 1, and then we can actually rewrite it in this form. So first we enumerate every leaf of the protocol pi, and then okay, for each leaf, okay, pi on input of that leaf is fixed, so we can extract it out. So then we sum over all the inputs in that leaf. Okay, so idea is follows. So if we can bound the sum of this, then okay, we say okay, if let's say if the absolute value of this sum is at most let's say 1 over m, then we need m leaves to make this close to 1. So we can define the discrepancy as follows. So for actually we know that okay, for each leaf this space is actually an affine subspace. So we can define the discrepancy as follows. So for every f and mu and the affine subspace S, okay, we can just define the bias as this sum, and then we define the discrepancy as a minus log of this max bias, and this distribution-free discrepancy is just a maximum discrepancy over all the distribution mu. And it turns out that this discrepancy f mu is just a lower bound for distributional complexity with respect to mu, and this distribution-free discrepancy is just a lower bound for randomized parity decision tree complexity. Okay. Okay, so here's our second result. So we show that the randomized parity decision tree complexity of computing k copies of functions is at least k times discrepancy of f. Okay, so before showing the proof idea, so I want to compare our main results. So recall that okay, in our main results, we lower bound this randomized cost of computing k copied functions over k by d product f and the discrepancy of f respectively. And we show that, okay, these two results are actually incomparable. So we prove that, okay, there exists f such that the discrepancy is small and this d product is linear. And we also show there exists some function such that the discrepancy is linear, but D product is constant. Okay, so this is our second result. Okay, so now let me talk about the proof idea of our second result. Oh, sorry. So actually, we show something stronger. This XOR lemma for discrepancy. So here we prove that the discrepancy of XOR of k copies of F is k times discrepancy of F. Okay. Okay, the idea is very simple. So actually, there are very nice characterization of this discrepancy. It turns out this discrepancy is actually can be actually approximated by minus log, and the maximum Fourier coefficient of this function f mu, which is the normalized pointwise product of f and mu. So why this is true? For the lower bound, let's just fix an affine subspace S, and we can observe that the bias of F on this affine subspace is a weighted average of some Fourier coefficients of F mu. So it cannot be greater than the largest Fourier coefficient. And for the lower bound, okay, let's find the maximum Fourier coefficient. Let's see with this index S, and then let's consider, okay, we query this the XOR of variables with coordinates in S, and then this will give us two affine subspaces of codimension 1. So it's actually not hard to see one of them has bias at least this Fourier coefficient over 2, which is just the maximum Fourier coefficient over 2. Okay. So and okay, the rest. Okay, the rest of proof is kind of easy because we have already approximated this discrepancy by this minus log maximum Fourier coefficient. So we just need to prove this XOR lemma for maximum Fourier coefficient, and this is kind of clear. So yeah, this together just implies this XOR lemmas for discrepancy. Okay. So now I want to talk about more technical results of our direct sum for product distribution with respect to product distributions. Okay. Actually, to prove this direct sum for max depths, it actually suffices to just prove that for average depths. So let's see. So we define average depths of a tree as the average number of queries made by T, where input is sampled from the distribution mu. And we see, okay, the average parity dissymetry capacity of a function is just the minimum of this average depth of the tree, where the minimum is taken over any randomized parity dissymetry that computes the function with error at most epsilon. Okay, so it is clear that, okay, this average depth cannot be greater than the max depth. And there's a folklore result saying that, okay, actually they are kind of equivalent. So for every f mu, and actually this max depth cannot be much larger than this average depth. And actually this result works kind of for every tree protocols. So idea is easy. So given a tree of average depth Q with respect to some distribution mu, and we can just shave all the nodes of depth greater than Q over delta. And the result tree should be delta close to the original one. So this is just by Markov inequality. So this removed part just cover at most delta fraction of inputs. Okay, so now let's do a warm-up. So let's consider the uniform distribution. So our plan is as follows. So let's first maybe fix an arbitrary parity distribution tree for k copies of f. And for each instance, we want to extract a randomized parity distribution tree, Ti, such that so the arrow made by Ti on f is at most arrow made by T on k copies f. And moreover, we want the average depths of T, sum of average depths of Ti to be at most the average depths of T. And then we can just choose T to be the parity decision tree that witnesses this measure. Then, okay, then we are done. So how do we construct this tree Ti? Okay, we can just simulate T. And for each node V, we let mu V denote the distribution of inputs that lead to V, and let mu Vi denote the margin of mu V on the ith instance. It's actually not hard to see that this mu Vi is uniform over some affine subspace Ci. So for example, let's just, for simplicity, consider a non-adaptive parity decision tree. So first, we make this query, and because this query involves with variables in two instances. So actually, after making this query, C1 and C2 will remain the same, the whole subspace. Okay, and then after making the second query, we actually learn something about the second instance. So we know that, okay, what is x2 for the second instance? And then after making this parity query, okay, then we can learn what is the single variable in the first instance, and the parity, all the parity information in the second instance. Okay. So then our strategy works as follows. So let's just consider, okay, if including the current query, we'll enlarge this complement of Ci, then we can just query an arbitrary vector in this extended region. And then we can infer the value of current query and proceed with the corresponding child. Otherwise, we just select the uniform random child and continue. So for example, so for the first query, because this C1 orthogonal is still empty, so we just okay, toss a random coin, and for C2, we do the same. And okay, for the second query, okay, C1 complement is still empty, so we still, okay, do a random guess. But for the second instance, okay, we include a new vector in this C2 complement. So we just query this x2. And for the third query, okay, so this C11 become larger, so we will query this x11, and for the second instance, we'll also query this x12 XOR x22. Yeah. Okay, so now we will somehow, yeah, recall that we want each Ti to satisfy this arrow guarantee and this depth guarantee. So for the correctness, we know that, okay, so this equation holds because and this Ti actually perfect simulates the global distribution tree on the ith component. And for the second item, efficiency, we know that actually at any stage, the sum of codimension of Ci cannot exceed the number of queries made by T. This is just some basic linear algebra. Okay, but both statements require mu to be uniform. Okay, so now I want to briefly talk about how we prove the arbitrary product distribution case. So as I just said, the aforementioned strategy does not work for general product distribution, since a global query can change the marginal distribution of a single instance. Even there's like no, you cannot extract pure queries from those global queries. So what we do is we reduce this uniform case to reduce this arbitrary product distributions to uniform distributions by decomposing each bit into a fixed bit plus a uniform bit. So to be more formal, so given a distribution mu, we can sample a random partial fixing as follows. So for each bit, we independently fix it to be 0, 1, with probability 1 over, with probability absolute value of 1 minus 2 mu I, and the fixing depends on, okay, if the bit is more biased towards 0 or towards 1, and otherwise we set it to be uniform. So for example, let's consider, okay, we have this vector mu vector that describes mu. So each entry is a probability that each bit, the probability of each bit equals to 1. So, okay, so we can sample the random partial fixing as follows. For the first entry of the fixing, so it equals to 1 with probability 0.4 and star with probability 0.6. And for the second bit, for the third bit, we can we have a similar thing. Okay. Now we need to define a tree, T row, which is the tree obtained by applying this this partial fixing on T, and then removing redundant queries. So for example, I have a tree here, and let's consider the random partial fixing 0, 1 star. So after applying the on T, we will get a decision tree just query x3 because x1 and x2 are fixed. So the key to our proof is a measure for which we call skewed measure. So it is defined as follows. Given a parity decision tree T, we can define this SQT as the expected average number of queries made by T row. So here row is just over all random partial fixing. And here the average number of queries is defined with respect to uniform distribution after fixing the bits in the support of row. And then for any function f, then we can define this skewed measure, which we denoted by S as the minimum of SQT, where the minimum is taken over any parity decision tree T that computes f with error, let's say, at most 1/3. Okay, so, and then to prove the direct sum with respect to product distributions, we only need to prove the following two lemmas. The first is direct sum for this skewed measure S, and it's actually, the proof is just almost identical to the uniform case. And actually, if mu is uniform, this skewed measure is just the average depth. And the second lemma is showing that actually this average depth cannot be, we know that, okay, average depth is at least S, but we show that, okay, average depth cannot be much larger than S. What we show is average depth is at most log n times S. And this together imply the sum for distributional periodization complexity with respect to product distributions. And here I also want to remark that this log n factor here is necessary, just for this bound. So somehow, we cannot remove this log n factor in this for this approach. Okay. Okay, so I just want to mention some open problems. And so first one is to extend our result to arbitrary distributions. And second one is, can we prove some direct product for periodization trees? And third one is to prove deterministic direct sum for periodization trees. Okay, thank you.